Hey everybody, so here is our last lesson or whatever in this series that has to do with wave behaviors and how waves interact with each other. Um, this one is like totally in the wrong spot. Interesting. No, I guess not. So anyway, we're looking at wave interactions today, how waves interact with one another, and then how waves interact with different boundaries is kind of the theme of today's lesson, this vast last little part of this. So on the screen right here, you can see some pictures of the first phenomenon that we're going to take a look at today, which is interference, and how interference is how waves interact with each other. So when a wave meets another wave, what does it do? And all the pictures that are on here actually have to do with this concept of interference. Some of them are good and some of them are bad. So interference could be like the big water waves in the middle where two waves meet one another and then just explode in their hugeness. Most commonly, interference is used with that kind of electromagnetic interference, like in the TV screen on the top left. But interference is also, why they make you turn off your phones when you get on the airplane. It also has to do with that picture in the top right is actually the thin film interference and diffraction that occurs on soap bubbles, and the different ways that the light waves interact with one another through that curved surface of soap as it's changing. And then water ripples is a good example of interference, how the waves interact with one another, and the different colors, the light and the dark ripply patterns that you get from that. And then noise canceling headphones actually directly takes advantage of interference on purpose in order to make to basically block out outside sounds. So anyway, it's definitely a part of a variety of different options that are out there. So for this, in terms of wave interference, the couple of key things that you need to know. Number one, interference is, like I said, it's when any two wave pulses come into contact with one another. When they meet one another, there's two important things. Number one, the moment that they meet, there is something called superposition. Literally, the two waves are on top of one another at the same time. Superposition is additive. In other words, when those two waves meet one another and are on top of one another, the amplitudes are simply added together mathematically. So if this one was, say, for example, come on, give me my pen, a plus 10, and this one was a plus 5. By plus, I mean above the equilibrium line as opposed to below. Then the total amplitude when the two meet for just a second is going to be plus 15. Again, this is part of how this principle of superposition works. So that's an important one. First of all, superposition is an additive process. The second thing is that what happens after they meet is that the two wave pulses will just literally pass through one another. They do not change their nature, their behavior, their size, anything as a result of that interaction. So that superposition is really a very momentary state where it's just that instant where they're on top of one another, they get super tall, and then they continue on through one another without being changed in the process. So again, that is called the principle of superposition. This also works when you have wave pulses that are going in opposite directions. It's still an additive process. It's just some of your addition is positive numbers and some of your addition is negative numbers. So in this one, in this kind of left sequence here, you can kind of imagine these two little wave pulses are approaching one another. They're getting closer. There's that moment of superposition where you get this doubly tall wave crest. And then the tall pulse continues its merry way to the left, and the smaller pulse continues on its merry way to the right as it continues. The same thing happens if you have positive and negative waves. So this one has a positive amplitude, and this one's got a negative amplitude. Again, there's opposite directions. One's a crest and one's a trough, if you want to think of it that way. A trough is simply a negative amplitude crest. And then the same thing happens when these two guys approach and meet together here in the center. You can see that if this one was like plus 5 and this one was minus 10, then that means that according to the principle of superposition, your amplitude of superposition at that point would simply be the sum of their two amplitudes. In this case, would be like negative 5. You can have the case where if I had like this one coming up and then this one coming up like that, if this one's plus 5 and this one's -5, then according to the principle of superposition, when these two meet, you will get an amplitude of 0. They will literally cancel one each other out for just a moment. This is how noise canceling headphones actually work, is that it reads the incoming wave pulses and then generates kind of the mirror image wave pulse, so that those background noises literally just cancel each other out and you get noise cancellation. So again, this is called superposition, and it's simply an additive process. So with these two things, if they add together and result in a larger amplitude, this is oftentimes called constructive interference. This specifically happens more when you don't just have a single wave pulse, but when you have a standing wave pattern, when you have waves that are continually making pulses repeatedly so they can bounce back and add up, and you get this sort of multiplied effect. And again, so constructive interference is the name of that pattern when you've got generally positive interactions of those two. And then this one over here on the right, where they cancel each other out, is called perfectly destructive interference, perfectly destructive, or complete cancellation. You can have moderately destructive as well, where if you have one that comes up and one that goes down, you can have your resulting one is just a little bit of amplitude. That would still be considered to be destructive, just not perfectly destructive, or complete cancellation. So again, you can have anywhere in between, and if you get a lot of really chaotic patterns. These two are both kind of perfect examples, typically truly textbook examples of perfectly additive constructive interference, where the two waves have literally the exact same crest at the exact same time. You can get some really chaotic patterns that almost kind of look like this, where you kind of get some like really weird, and then here would be your kind of middle line, where you can get some really complicated wave patterns. So think about how waves like water waves work. You don't get truly smooth constructive or smoothly destructive. You get these sort of chaotic ripple effects. By the way, with constructive interference, typically you'll get like bright spots and dark spots. So you see this with ripples on the lake a lot of times, where you'll get water ripples where they'll be kind of like, this would be just sunlight going through still water hitting the lake bottom. This would be sunlight going through ripples, where you'd get bright spots, high intensities, and dark spots, shadows, basically, even though it's perfectly clear water both ways. So again, if you can think about being out in the lake in that beautiful clear water, where you get those interesting ripple effects underneath, where you get like kind of neutral light levels, super bright, super dark, and that's what you can kind of get from that sort of case. So constructive and destructive interference are simply names that we assign to particular types of superposition patterns that we see. Okay, moving on. Next kind of set of interactions here. Again, interference is all about two wave pulses meeting one another. Reflection, it's a commonly known term, I know you know this word, is more about what happens when a wave or a wave pulse hits a boundary or hits a change in media. Again, media or medium is the material that the wave is traveling through. Reflection is most commonly used when a wave is traveling through a medium and hits a fixed edge where it cannot pass through, although reflection happens at every boundary. So all of these pictures on here are examples of reflection and how reflection gets used. So for example, radar is the thing that's at the top left. It's actually sending out electromagnetic radiation that's hitting things like clouds or satellites or whatever, and bouncing back. So you're actually reflecting off of something in the sky, typically. Radar, in terms of this one at the bottom, the cruise control, is actually another form of radar, where you're literally using different, it could be sound waves too, but you're usually using a type of electromagnetic radiation to detect a vehicle in front of you, and the rate that it's bouncing back at you, combined with something called the Doppler effect, can tell you whether or not the car is in front of you is holding still, whether you're approaching it, or whether it's pulling away from you. But again, it's still based off that concept of reflection. The waves are going forward from your car and then bouncing back, and you're reading the time it takes for them to return. Simple echoes, like this gentleman yelling off into the canyon here. A simple echo is a type of reflection. It's a reflection of sound waves, where you're sending sound waves off, they're hitting a wall on the other side, and they're bouncing back towards you, and you're hearing them a second time. We're used to sound being a one-way production, but reflection of sound waves produces that secondary pitch, secondary sound. Bottom left here, this is sonar. Sonar, and same thing with our bat here, friend, is sonar. Sonar and radar work under very similar styles, just a different type of wave is being produced. Sonar is specifically done with sound waves, as opposed to radar is typically done with radio waves, which is a type of light. So again, with these, you're sending off, it's essentially an echo. It's just an echo that you can't hear with the naked ears, just like you can't see radar with the naked eyes. So sonar would be, detecting to the bottom and hearing the echo coming back up. Bats fly around based on sonar all the time, and they can detect when there's little bugs and stuff off in their future. And then the typical one, the easy one, is reflection of light. That's the one that everybody knows about. This is the bean. It's a big sculpture in Chicago, a place close to my heart. But reflection of light. So light is hitting that surface, and those light waves are bouncing back to you. So you're actually seeing a funky curvature to this, the weird reflections to it, because that surface is not flat, so you don't have perfect reflection to it. So again, with this type of wave interaction, again, it's about a wave pulse or a wave form of a bunch of repeated pulses hitting a boundary. So the nature of the boundary here is important, and that's the next two slides. So if you talk about it hitting a fixed boundary, so like hitting a wall, this, when it bounces back, tends to bounce back inverted. And that's the key concept here that I want to make sure that you get, that every time a wave hits a boundary, it's going to bounce back. If that boundary is a dense boundary or a fixed boundary or like a wall, it's going to come back. That wave pulse is going to come back upside down, and that's going to create some different sound pitches and things like that can have to do with some of the effects that we see. But it definitely does come back upside down. So that's an important part about this. Typically, spherical chicken assumptions, if there's no friction or anything else, it should come back with the same amplitude but negative. Whether it actually does, again, is based on things like friction and all kinds of other losses of energy in other formats. But again, spherical chicken, without any other interaction of any sort, it should come back inverted. If this has got amplitude of A, then the inverted one would have an amplitude of negative A, come back upside down. Now, if it bounces against a soft boundary, and this is a little bit weird to think about what this is, soft boundary would be something that is less dense. In this case, it's kind of weird to picture this because it's not like an everyday kind of circumstance. This other one would be, imagine like you've got a string tied to like a dowel, and you just do a whip, like a typical motion that you'd have, and that other end is literally fixed in place. With this other style, you have to imagine that this other end is free to move up and down. So this is just a loop as opposed to a knot. Again, not a normal circumstance. You can imagine a whip if there is nothing on the end for it to bounce back to. It's a little bit harder when you have just the end of the rope, but it's just sort of bouncing back against air, and it's not a lot of everyday examples of this one. But in this particular case, if that is a loose end or a low density end, it's free to move, then now when it reflects back upright. So whatever your amplitude is going in, you'll have the exact same amplitude coming back out. The velocity is negative, it's going back the other direction. But again, this is based on the two boundaries. So this can also happen in cases when the pulse is traveling through. So not just with reflection, this can happen with other types of reflection as well. So I'm going to show you this next one. This is definitely a really weird I have another one on the way. I'll come back to that other idea. So anyway, the two big ideas. Fixed boundary is inverted. If it's a soft boundary, it's going to be upright. Again, it's a little bit backwards from a lot of what students think, but the nature of the boundary itself is really important to how the reflection works. If it's a hard boundary, it's going to come back inverted. So with this, sometimes when you have things and they bounce back, you can get some really cool standing patterns. So the easiest concept of this standing wave is a jump rope. And you can kind of see it. It's a little bit brief, hard to see in this particular picture right here. But imagine a jump rope where you've got one end is fixed in one person's hand, the other end is fixed in the other person's hand, and this rope is just literally circulating around. You've got two vocab words that go along with this, which is the terms node and antinode. The nodes are the fixed spots. They basically don't move. The antinodes are zones of maximum displacement. So that's literally where the jump roper would be. You can have more than one node and antinode. So you can kind of see there's a spot here where a dude is spinning one end of the rope. Here he is, and he's literally spinning it like this. And on the other end, there's a little fixed spot right there where that other end of the rope is attached. So we tend to think of jump rope as having a single antinode and two nodes, the nodes on the two ends. Here he's spinning it just fast enough that he actually has two antinodes. There's an antinode here and an antinode here. You can imagine that if we watch this animation, it would look like this, where you'd have an up spot, then you'd have a fixed spot, and it's not truly fixed. It just is like a zone of minimal movement. It looks like it's holding still right there. It's an optical illusion. And then you have another kind of maximum spot, kind of like this drawing is on here. And so you can kind of see in this little picture over here, there we go, we have some other standing node patterns. So here you've got that same thing where you've got a node and a top and the bottom, always have a node there. And this one's got two antinodes and a node here in the center, right? This third one, if you spin it even faster, you get nodes at the ends, and then you've got a couple of nodes in the middle, and then again, two antinodes actually at either end as well. And then if you spin it faster yet, you can get 1, 2, 3 nodes in the middle, 1, 2, 3, 4 antinodes, and you actually have 5 nodes total, 2 at the either ends. By the way, this one is actually really interesting because it's not actually a string. If you take a picture of strings, they will do this. So when you talk about like a guitar string, it'll actually do these kinds of vibrations. And when you touch your fingers here and here, like at the frets, you can actually get harmonics. That's the whole idea about sound. But what these are actually pictures of is some quantum behavior. Believe it or not, these that's why these pictures look so fuzzy, because these are actually submicroscopic pictures. And just as a note to self, a particular type of standing wave is actually the concept that you know from chemistry called electron orbitals. And that's kind of where this comes from. This is a quantum behavior that when you get electrons, which actually behave like waves as well as like particles, their vibrational standing waves are what we call orbitals. They're not linear, so that's why they don't have this kind of a shape to them. They're actually more of a circular or cloud shape. And so we get these different nodes and antinodes so that you can kind of see and hear what some of those spaces would actually look like. So anyway, just an aside. So standing waves, what you end up getting, the reason why these work is because you send a wave pattern here, hits this node on this end, or hits that boundary, say, for example, on that end. Give me my pen back. Come on, give me my pen. Give me my pen. Come on, pen. There we go. Okay. Hits this boundary right here. So imagine I make a wave, boom, comes like this, hits this boundary. If this is a fixed boundary, it's going to bounce back reflected and inverted. So it's going to bounce back this way. So you can think of it as being kind of a directional sort of thing where this one's going this way, and then this one is the reflected wave coming back this way. And if I keep going and I keep making that pattern, eventually you'll make this thing will kind of sit in place. If you haven't had a chance to do this, play with a piece of string or a slinky. Actually look up slinky standing waves on YouTube, and you can see some really good videos of what that looks like. All right, moving on, so don't take up too much of our valuable time here. You can also get, and this is kind of our third phenomenon, is you can also get transmission through boundaries. If you have soft boundaries of certain types, that wave can not only reflect back at the boundary, but it can travel through the boundary. So the best way to think about these images on here is like two pieces of rope, a thick piece of rope tied to a thin piece of rope. Again, not something we have lying around our house, so it's a little bit of an odd thing. But if you have an incoming, right here, if you have an incoming wave on a light material, and then it hits this heavy material, this heavy material is going to act at this boundary right here. Come on, give me my pen. That boundary right there is going to act like a fixed boundary because it's going from something lighter to heavier. So it will reflect back inverted, but it will also transmit through. And it's important to know that the transmission through is going to still be the same thing. It's always upright when it transmits through, or it's the same direction when it goes through. It's a little bit smaller here because of the loss of energy as it's bouncing back and traveling through this thicker material. If you think about it going the opposite direction, here it's starting in this heavier rope and traveling to the left. So when it goes from this heavier rope to this lighter rope, that's going to act like a loose or a soft boundary. And so when it passes, when it reflects back, because it's reflecting from a softer boundary, it's going to reflect back upright. And it will, again, also transmit through. So it'll go through those boundaries because it's not really a wall. It can transmit across that. And this is actually called refraction when it does this. I'll get to that on the next slide. It always passes through upright. It's, again, whether or not it reflects back upright or upside down is based upon, again, whether or not that boundary is acting like a heavier boundary, a fixed boundary, or whether it's acting like it's going into a lighter medium or a soft boundary. And you can kind of see the same thing is directed over here on the other side. So as I alluded to, this other mode, this idea of, this is phenomenon number 3, is not reflecting off a boundary, but reflecting sort of through a boundary, transmitting through a boundary and changing some of its behavior because it's changing what it's going through. This is called refraction. And it's really hard to say reflection and refraction. One's got an L, one's got an F in it. So be careful of that. Refraction means that the wave is traveling through different media. Reflection means it's bouncing off. So if you take a look at one of these, if it's coming in this blue heavy rope right here, this wave over here is the refracted, sorry, I said it wrong myself, the reflected wave pulse. This one that's continuing on now with some slightly different characteristics is the refracted wave pulse, because it's going into a different medium. And what light does, and what all material does, is because it's traveling through different media, it actually changes its speed. And that changing its speed can have some other effects on it. If you think about this, you can see it really clearly here that this light wave bends. This is actually a lab that we would normally do in a couple units out from now. But it's coming in at one angle, and you can see how it bends. It's not a straight line anymore. It's because the light's traveling faster through the air and slower through this. This is acrylic or plastic. And then it's traveling faster again. And so that change in speed tends to change its direction. With the rope, for example, the change in speed and the change in energy tend to change the amplitude. So it kind of depends on what type of wave it is. But you can really clearly see that refraction right there, that there's a big difference between how the light is bending through the water versus how the light is bending through the air. And you get these weird optical illusions that go along with this. And again, this is due to a change in speed. And we see refraction in all kinds of waves. And again, that changing speed sometimes changes the direction of the wave. Sometimes it changes the amplitude of the wave. Sometimes it changes the frequency of the wave. It depends on the kind of wave. We'll get more into that later. But the key ideas here is this, and we're summarizing, wrapping it up, and we're done. So interference is when two waves or two wave pulses meet one another, and what do? It's governed by the law of superposition. It's literally just an additive process. If they add together and get bigger, it's called constructive interference. If they add together and get smaller, then it's called destructive interference, or it could be complete cancellation if you wish. Then we have the idea of what happens when waves interact with boundaries. So those boundaries could be a hard boundary. It could actually be any kind of boundary, but anytime a wave hits a boundary, it will reflect at least partially. Even if it's a soft boundary, it'll reflect back partially. The idea about upright or inverted, again, if it's hitting a hard boundary, it's going to reflect inverted. If it hits a softer boundary, it'll reflect back upright. That if you get that reflection timed just right, you can actually get standing waves, which is a combination of the idea of reflection with timing, and actually includes that idea of a resonance, right? Because if you're adding that reflection back at just the right time, you'll actually get a magnification and amplitude, almost like a type of a constructive interference, which is similar to the idea of resonance that goes along with standing waves. And then last but not least, if you have waves that are transmitting through a boundary because of the nature of the media that's on there, then we can take a look for that phenomenon of refraction, changing speed as it transmits through a change in media. Again, sometimes it just bounces off, like reflection. Light only is going to bounce off a wall. It's not going to really transmit through the wall. But if you're talking about glass, for example, light is going to both reflect off the surface of the glass and transmit through the glass. And when it transmits through glass, because it's going through a different medium, it will change its speed. And that phenomenon is called refraction. So there you have it. Wave interference or wave interactions, wave behaviors, I guess, either with each other or with their media. So I hope you enjoyed that, and good luck with that last part of your homework assignment. And I will be seeing you guys possibly in just a few minutes at one of our online meets. So there you go. Have a good one, guys. Take care.